Yo, 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 I'm back. Grandmaster C here, and you have seen me in such fine quality chemistry educational videos as Stoichiometry and You, Part 17, and check out that stoic going down the street. Alright, in this stoichiometry video, I'm going to show you guys the full-on stoichiometry on this. And we have an equation here. We have ourselves a problem where we are given the mass of our reactants, and we got to figure out the mass of product that we've got. This is it. This is where we get to use all those tools. Calculate how many grams there are in a mole of something, change from moles of reactant to moles of product, and then with moles of product we can figure out how many grams. So it's kind of a very interesting thing here. So let's take a look here. If you have 300 grams of NH3 and excess O2, how many moles of NO are made? Okay, well, we have 300 grams right here. Okay, fantastic. And they say excess O2, check. And they say how many moles of NO are made? Okay, good news. Notice they didn't say anything about the water. Guess what? If they don't say anything about the water, then we can safely cross it off. Yay! Now notice it says excess O2. Okay, what does that mean? Well, excess, remember, excess, the idea behind excess is you got lots and lots of it, you won't run out of it. You are going to be running out of the ammonia before you run out of the oxygen. Yep. So guess what? Do I need to worry about the oxygen? Nope. Now I can concentrate on this and this. That's it. Okay, where do I begin? Well, you know what? I can't tell how many moles I'm going to have of my product unless I figure out how many moles of reactant I've got in the first place. And I can't tell just by looking at the mass. So I need to figure out something. I have to go from grams to moles of the NH3. How do I do that? If I go from grams to moles, I need to divide. Okay, but wait a minute, what are you dividing? Okay, well, we're going to take our 300 grams that we have, and we're going to divide it by the however many grams there are in a mole of NH3. Now, wait, what about the 4? That doesn't play into it. When you're going from moles to grams or grams to moles, the coefficient, in this case the 4, does not play a role in it. The only time that 4 is going to play the role is when we look at, here's how many moles of ammonia we got, how many moles of NO are we going to get as a result. That's it. That's the only time. So we don't have to worry about that. Wait, I forgot how to do the grams per mole. Not a problem. Got you covered. You can see that in an earlier video, but very quickly, without looking at the periodic chart, I'm going to go ahead and say that nitrogen is 14.01 grams, and then hydrogen is 1.01 grams. How in the world do I know this? Okay now, anytime. I'm losing time, people. The periodic chart. So when I never need to know how many grams there are in a mole of any element, I use the periodic chart. But I gotta go back. So I'm going to go ahead, and since nitrogen is 14.01 and the hydrogens are 1.01 each, I just need to add them up, and I've got 17.04 grams per mole. So now I'm going to take my calculator and I'm going to divide 300 divided by 17.04 grams per mole, and I have got 17.61 moles of NH3. Okay, that's all right, I guess. That's not quite a pound of ammonia that I'm looking at, But that's what we needed. And you'd say, well, why do we need to change this from grams to moles? The idea, guys, is we have to do mass of our ammonia. We had to change it to numbers of ammonia, because then we can take the numbers of ammonia and figure out how many numbers of NO. That NO, that's what we're looking for. We can't take the mass of ammonia and go and figure out how many moles of NO are we going to get. We can't do that. You can't take the mass of something and figure out the numbers. Remember in class I made the analogy of tires. If I've got 5,000 kilograms of tire rubber, how many cars am I going to outfit? Well, wait a minute. How many tires am I going to make with 5,000 kilograms of tire rubber? Well, I need to know how many kilograms of tire rubber does it need to make one tire. And that's what I'm doing here. That's how many it's like how many kilograms of tire rubber I need to make one tire, just like I have 17.04 grams per mole. That's what I need. And here's what my 5,000 kilograms of tire rubber, in our case here, 300 grams of ammonia. And then we figure out, okay, this is how many tires I was able to figure out. In this case here, the moles of ammonia. Remember, the mole is a giant number. Think of it as the chemist's dozen. Now we're ready for the next part. The next part, we got to figure out, we're going to go from moles of ammonia to moles of NO. That's our target. Okay, so we need to look at our equation. And the equation says, according to our equation, it says for every 4 of these ammonias, these NH3s, I get 4 of these NOs. Okay. So if I have 4 of these NH3s, I know I'm going to get 4 of these NOs. Okay? So I have that. Now I happen to have 17.61 moles of NH3. Now remember the idea, this is a ratio. It's like saying for every 1 car, you need 4 tires for the 1 car. And that's what we've got here. For every 4 of these NH3s, we get 4 of these NOs. So how many moles of NO are we going to get? Well, this is going to be pretty straightforward because it's a ratio, and you can go ahead and cross-multiply and divide. You can do that. Now, in this case, it's pretty straightforward because what you're seeing here, you're going to get the exact same number here. So our final answer, ladies and gentlemen, 4x is equal to 4 times 17.61. Okay, so I multiplied it out, and now I'm going to divide both sides by 4 because we got 4 on both sides of the equal sign, right? That's right. So x is equal to 17.61 moles of NO. So, ladies and gentlemen, this is our final answer for the first one. X is equal to 17.61 moles of NO. No. Okay, and again, if you're having difficulty figuring out grams per mole or moles per gram, you can go back to the earlier video. I do explain that in more detail. Okay, I'm going to go ahead and work with the next one. So here we have a very similar problem. We have 50 grams of NH3. Okay, I'm going to write that up here. 50 grams of NH3, 50 grams of O2. Okay. How many moles of NO are being made? Well, you know what? I'm going to change that because I want to know how many grams of NO are being made. This is an example of a mass-to-mass stoichiometry problem. Okay, now the last example, we looked at it and we said, okay, we've got grams of ammonia, excess O2, how many moles of NO are we going to make? So we're still going to work with NO, okay? We're still going to work with that. But now this time we've got the oxygen in there. Now do we need to worry about the water? Nope, we don't. Water is considered a byproduct. It's a product as a result of this reaction. We burned ammonia and we got water vapor that's going off, and honestly we don't care about that. Okay, we don't. So now we've got this left over. Okay, Now this is going to require a little bit more work because, again, we can't take a mass and figure out the mass of product based off of this, the mass of our reactants. We can't. We have to change the mass, or the weight, if you want to look at it that way, into numbers. We can compare numbers of product and numbers of reactants to see what are we going to get. So we're going to go ahead and we're going to change this from grams to moles. And we're going to do the same thing here. We're going to change this from grams to moles. Now, in both cases, we're going to have to divide. Okay? Then we're going to look at this, and then we're going to be able to figure out how much no are we going to make. Because one of these two is going to run out. And that is where you get the idea of limiting reactant. Because so oftentimes, in any manufacturing process, you're going to run out of one particular reactant or one particular ingredient. Usually it's going to be your most expensive ingredient. That's going to limit you on how much product you're going to make. Okay, so let's take a look at this here for a moment. So we already know, ladies and gentlemen, here it's going to be 50 grams divided by, okay, that's going to be 17.04. Again, where did I get those numbers? Where did I come up with this? Well, remember, there's 1 nitrogen and 3 hydrogens. You take a look at your periodic table for your hydrogen and your nitrogen, and you add them up. Okay? So now, we move on. So we got 50 divided by 17.04. Let's keep going. 50 divided by 17.04 equals, and I have, okay, 2.93 moles of ammonia. Great. What else can I do with it? Well, let's see how much product I'm actually going to make. Okay, so I have 2.93 moles. So according to our reaction that we had earlier, and let me scroll that back so you can see, it's 4NH3 to 4NO. So like our last example, if I have 4 NH3s, here I have 2.93 NH3s, that's going to equal 4 NOs over, well, we don't know how many NH3s, how many NOs that we're going to get, right? And again, this is where you're going to cross multiply and divide. Now, the numbers work out pretty well. And what you end up with is that if we burn up the hydrogen, and we assume there's lots of oxygen, because that's what we're doing, we're assuming we have plenty of oxygen, it would be like in excess, we're going to get 2.93 moles of NO made. So according to the hydrogen, we would get 2.93 moles of NO made. That's only part of the story. But now we got to do the second work. And the second work, ladies and gentlemen, has to do with, okay, what about the oxygen? What about the oxygen at this point? And I'm going to switch to another color. I'm going to switch to green. So, in this case here, for our oxygen, they gave us 50 grams of the O2. All right. So, I have 50 grams of O2. Okay. And I know that there is, okay, I need to check my periodic chart because I got to go from grams to moles of O2. So that basically means, ladies and gentlemen, we're going to take 50 grams and we're going to divide it by how many grams there are in a mole of O2. Okay? So let's see. Well, each oxygen is 16, and we can check the periodic chart right here. There's 16 for the oxygen, so we're good. So 16, and there's 2 of them, right? So 16 plus 16 is 32. Now, some people would say, but wait a minute, Mr. Canu, what about that 5? Do we need to put that in there? No, 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 no. That's the coefficient. You don't put that in when you're changing moles to grams and grams to moles. You don't. The only time you got to worry about that is when we have to figure out how many moles of no are we going to make. And some people would say, no. Yes. Yes, that's what it is. So we go in, so let's see. Oh, okay, 50 divided by 32, and we get ourselves 1.56 moles of O2. So we have 1.56 moles of O2. Great. Now we have figured out how many moles of O2 that we've got. Now we need to figure out, we have the numbers of O2, now we need the numbers of NO. So let's take a look again at our original equation. I'm kind of running out of time here. There's 5, that's where now the coefficient comes in, 5 to 4. Okay, no problem. So I have here 5O2, and here is 4NO, okay? And now, based off of our calculation, we got 1.56. 1.56 moles of O2, and we don't know how many moles of NO are we going to get. Now in this case, unlike the other example, where it was pretty easy, you still need to cross multiply and divide. That just makes it a little bit easier for everybody. So when we do that, we get 5x is equal to 4 times 1.56. That's what we have. So 4 times 1.56 equals 6.24. So 5x is equal to 6.24. Now, let's go through, divide both sides by 5. X is equal to 6.24 divided by 5. Okay, 6.24 divided by 5 equals, and that is going to get us 1.25, I'm rounding up, moles of NO are made. So, that would be a big deal, because let's see what we have here. We figured out that with the hydrogen, with the ammonia, burning it up, assuming oxygen's in excess, we get 2.93 moles of NO are made. Okay? Then we go with the oxygen, burn up the oxygen in excess NH3, the ammonia, and now we have 1.25 moles of NO are made. Now the question comes down to, okay, now I know my numbers. I've got 1.25 and I have got 2.93. Which one am I going to use? Okay, you go with the lower number. Here's why. Because one of those two reactants, or ingredients, if you will, of the reaction is going to run out. And once it runs out, the reaction stops. Nothing else is going to be burned. Not that day. Unless you add more stuff in, but that's a totally different situation. Okay? So now we're going to go with the 1.25 moles. Okay? So we have 1.25 moles of NO, and we got to figure out how many grams there are, and I've got to wrap this up very rapidly. So if I'm going from moles to grams, I have to multiply. Okay, so it's going to be 1.25 moles multiplied by, how many grams are there in a mole of NO? Well, let's see. If N is 14.01 and O is 16, that's going to give us 30.01 grams. Again, I get it from the periodic table. Okay, so this is what we have, and I got to go in, clear 1.25 times 30.01 equals 37.51 grams of NO are made. And ladies and gentlemen, that does conclude the video for today. I hope you got something out of it. And hey, I'll catch you the next time. Ta-ta!